Okay. So it's good to see all of you. Last lecture today, we made it. Of course, there's still lots of work to do, I suppose, for you and me both, but at least in terms of actually talking through the book, working through, a crazy number of chapters, 9 chapters. So great work, staying with the material, and we'll have Zoom office hours today, review session tomorrow to help you all look over it again and then get ready to demonstrate your knowledge of all of this. Okay, so today I just want to finish getting through chapter 19, and then we're going to briefly talk about chapter 20, and I have highlighted the slides that are actually relevant. But there are some extra ones depending on how much time we have that we can potentially go through. So we left off just talking really quickly about this idea of power, which describes how strongly the light is bent by a lens, and myopia and hyperopia, which are the two major ocular conditions in people that require vision adjustment. And we'll see this more in chapter 20, although some of it has to be skipped for purposes of time. But for a normal eye, if the muscles in the lens are relaxed, then the person will be able to focus light that's infinitely far away. So as we've seen in the thin lens equation, we have 1 over s plus 1 over s prime equals 1 over f. So if something is infinitely far away, some object, then the light will just be focused and form an image at the focal point. So f equals s prime. So for the case of a relaxed eye, so when there's the least strain on your eye, that corresponds to this situation where your focal length is the same distance as the image length. And so the light coming into your eyes that's actually being focused is light just really far away, basically, where the rays are nearly parallel. But your lens can actually be adjusted, and this is why you can look at things and form images of objects that are far away or of objects up close. When you make that transition, muscles in your eye are actually tugging on your lens in order to change its shape, so similar to the lens maker's equation. And so long as they hold that shape, you'll be able to focus some image at a closer point. So we can allow S to go, to not be infinity, to be something closer. And in that case, S prime will be, some complicated function of F and S, right? It'll be related to F and S, and we have to actually use the thin lens equation to find, what this new focal length would have to be in order to have light properly focused at the back of the eyeball. And so in people who have some vision problem, for example, I have myopia. So for me without glasses, this far point is significantly closer. So my eye can adjust its focal length, but even when it's not adjusting it, when it's totally relaxed, the light that comes in and forms an image at the back of the eyeball is significantly closer, only 50 centimeters away. And so that's about where you can see things clearly. If you're nearsighted, that's the limit to where you see things clearly. And then as your eye strengthens its focusing abilities corresponding to things getting nearer to you, someone with myopia can actually focus things closer than this typical 25 centimeter near point. So this is where it's good to mention this idea of a near point, which is the closest that your eyes can adjust their focal length such that you can still see an object clearly. So you can find it yourself just by taking your hand, holding it out and seeing it clearly at arm's length. And then as you bring it closer, eventually, maybe around here, it starts to get kind of blurry. This is the near point of your vision. And so if you do have some vision correction, you can try that with and without your glasses. And if you have myopia, you should have a near point significantly closer, basically because your eye is already sort of misfocusing parallel rays of light. So by the time you get up close, that extra focal adjustment due to the muscles on your lens is able to capture and focus that light up to a much smaller object length. And the situation is reversed for so this is a picture with a corrected myopic eye, so that just becomes a normal range of vision. That's the goal by adding that extra diffracting lens. And then the situation is reversed for hyperopia. So for hyperopia, you can see infinite, from infinity to some near point, but your near point is significantly farther away than a typical person's. Okay. And while we're on this topic, it's good to just mention that whenever your eyes do have to, increase their focusing power, so change the shape of your lens, that's why we experience this feeling of eye strain, like when you try to read or look at a screen for a long time. Your eyes just aren't designed to be able to hold that different focal length corresponding to a clear image for something up close. So they're not able to hold that for forever. And so eventually you'll feel those muscles tiring out. And so their relaxed state is where you're looking at things that are far away. So it's good to take breaks and look at things far away. That's why going on walks is a nice, break from studying. Okay, so we're going to quickly go through spherical mirrors. This won't be on the final, I've decided, but it is something that comes up on the MCAT and that I want you to see in this course, just because it's really not too much more difficult than thin lenses. And in fact, we're able to use the same equation to describe both spherical mirrors and thin lenses. So on the left, we have an example of a concave mirror. So what we can imagine is that if we have a sphere and we cut out a chunk of it, that if the light is shining on this side, that's a concave mirror. And if the light is shining on this other side, that's a convex mirror, similar to the one on the right here. This picture on the right is an M.C. Escher painting, one of my favorites from him, that he spent some painstaking amount of time very accurately capturing the way that an image is distorted in a convex spherical mirror. And so we can first look at the concave mirror, and you see that if we shine parallel light on a concave mirror, so that's these rays here, that they will all bounce off and come together at some focal point. So just like the case of a lens, for a spherical mirror, we have a focal point. It's just that that focal point is on the same side. So, the focal point that the light rays end up on is on the same side as the image. This is the idea, the primary difference between a mirror and a lens is that a lens allows light to pass through, so the light will go from one side to the other, whereas a mirror reflects light. And so those parallel rays pass through the focal point on the same side as they originate. And you can see that we can, now that we know that there's a focal point, we can draw the same three primary rays. Okay, so we have our first ray that leaves the object going parallel and then ends up passing through the focal point. It's just that now the focal point is on the same side as the object because it's reflective. We have our second ray, and so this is the ray that would normally go through the middle and not be bent. And so here we just use the law of reflection. So we say that this angle theta incident is the same as this angle theta reflected. So a little bit different on that ray, but a very similar principle. And then finally, we have the ray that goes from the top of the object, passes through the focal point, bounces off the mirror, and that ray will come out parallel. Right, so if it starts parallel, it'll go through the focal point, and if it starts going through the focal point, it'll come out parallel. That's the most important idea. And then whatever happens in the middle, that center point of the mirror, it's just as if the mirror is flat in that location, right? You can imagine drawing a tangent line here, and it would just be a flat mirror. So very similar to the case of the lens, where light traveling through the center, it experiences that as if it's just a flat piece of glass and it's not bent. For the mirror, we just say that it's, it is bent, but only by the law of reflection, not by any shenanigans with the curvature of the mirror. And so where all three of these rays intersect, this is where our image forms. And you can see that since the light rays are coming together to all meet at one point, that this is a real image. So we could put a piece of paper there and we would see that little projection of the tree. Okay, so these are examples of concave mirrors, right? The word cave can help you hopefully remember that these are sort of set inward, but we can shine light off the other side of the sphere and have these convex mirrors. Okay, so on this slide, we're looking at convex mirrors, and you can see that convex mirrors are more similar to diverging lenses. So we see that the light rays that come in parallel are going to bounce off this mirror and diverge, and that we could trace that reflected ray back and find a focal point on the other side of the mirror. Of course, the light doesn't go to that focal point. All of the light stays on one side of the mirror. It's reflected. But it's thinking about that focal point on the right side is a useful tool when drawing these ray diagrams, just like it is for a diverging lens. And so what we can do is we can think about these rays coming from the top of our object, from the top of this tree. And again, we have our three primary rays. We have one that starts off parallel and then gets reflected, and it's reflected in such a way that if we traced it back, it would come to the focal point on the right side. Then we have the ray that goes to, this is the one that goes as if it were going to the focal point. So it's aimed at the focal point on the other side, and it comes out parallel to the horizontal. And then lastly, we have the ray that just bounces off the middle, and that one is going to come out just using the law of reflection, so that our theta incident is the same as theta r. So it'll have just been, mirrored over that horizontal axis. And we can trace all of these back to find where they would intersect, and they intersect somewhere behind the mirror. So this is going to be a virtual image, right? The light that's reflected off of this mirror is diverging light. And so it's up to our eyeballs to capture that light and interpret it somehow. And our eyes interpret it by imagining that all of those rays originated at some point, which in this case happens to be behind the mirror. And our eye is like, oh, okay, that's where the light originated, so that's where the object is. And so that's how we get this virtual image right here. And you can see in this situation that the virtual image is smaller. And this is really beneficial in a few different applications. So we have this sphere here, which is just, something really pretty. But you see these mirrors on the side mirrors of cars, because they help to sort of condense the information in that vicinity. They kind of shrink it down into a small viewing area so that you can, drive while also monitoring who's beside you. Similarly, you'll see these in gas stations so that people can watch you while you're trying to steal candy bars or something. And that's, taking advantage again of these virtual images that are formed, where the surrounding environment is shrunken effectively, giving you a wider field of view in a smaller region, so that you can use this mirror to kind of monitor some area. Okay, and if we want to find, right, we can think about, we have some object distance s, we have some image distance s prime, or sorry, this is our, I always grab the highlighter. We have our focal length f and our image length s prime, and so we can write the thin lens equation. It turns out that these three variables, s, s prime, and f, are related exactly the same way for mirrors as they are for thin lenses, which is really crazy. But it all just comes down to similar triangles. I know I say mention similar triangles quite often, but they really are the basis of understanding both lenses and spherical mirrors because of the assumptions that we make about refraction and reflection in those systems. And so we just have to be careful, just like last time, to get the plus and minus signs right. So, for a one mirror system, so a one mirror system, S will always be positive. So the object length, we just call that positive. But F and S prime can be either positive or negative depending on our situation. So just like last time, we have a positive F for the type of mirror that focuses light, generally speaking. So F is positive for these concave mirrors that are able to focus the light and produce real images. Whereas F is negative for convex mirrors that create virtual images, right? They cause the light to diverge. So even this plus and minus convention here is very similar to the case of lenses, that basically the converging type thing is a positive focal length and the diverging type thing is a negative focal length. The weirdness now is that we have to remember we're dealing with mirrors, so it'll be natural for the image to be on the same side as the object, right? That's what's happening. That's what's happening in this picture for these concave mirrors. You can see that the image and the object are on the same side. They're both on the left of the mirror because it's a mirror. It reflects light. It doesn't let light pass through. Whereas in this situation, we have a virtual image where the two are on opposite sides. The object is on the left of the mirror, and this virtual image, which isn't really there, it's just a product of how our eyes interpret things, it's on the right side. And so that's reflected in the plus and minus signs of the image length. So for a real image, so S prime is positive for a real image, which means that it's on the same side as S, as our object length S, same side as S. And S prime is negative for a virtual image, which is on the opposite side, away from the object. And so that's really all there is to it. We still have the same magnification equation. That's just a product of like looking at these triangles and comparing this height here to this height here. And since we have the same relationship between S prime, and F, we have the same similar triangles. And so we can compare the height in the same way and just say that, this is the ratio of the height of the image to the height of the object. And I guess we should put a negative sign here just to make clear that this is negative in the case of inverted image. And the fact that it's related to the object and image lengths is just, like I said, a product of the fact that there's a one triangle for the object height and the object length, and one triangle for the image height and the image length, and that these two have the same angles, just they're differently scaled. Okay, so we have a sample question. A concave mirror of focal length F forms an image of the moon. Where is the image located? So we have our concave mirror, which means that light will be coming in like this. So for the moon, we have to think about how far away the moon is. Is the moon close or far? Right? Seems obvious once you think about it that way. So the moon is far. That's telling us that our object length is basically out at infinity. Our object is very far away. So you might ask, okay, Cannon, like, what if I have a really big mirror? Is the object still far away? Like, what if I make a mirror the size of the Earth? Is the moon still considered far away? And, no, not anymore, right? You're asking a good question if you ask that, because the size of the mirror and how far away something is, those two things we have to think about in context, right? So to figure out if something's far away, you want to be comparing the radius of the mirror to the distance the object is away. And if it's like many hundred times or more the radius away, then we would consider that pretty darn far. And so that would be the case for any realistic mirror we would build on Earth. The moon is quite far away, thousands of kilometers. And so any real mirror would have the moon with effectively an object length of infinity. Okay, so then we can write our thin lens equation. And when s goes to infinity, what happens to 1 over s? 0, exactly. And so where is the image located? Exactly, at the focal length. So that's just the statement that light entering the mirror going parallel will all be focused onto the focal point. Okay, and so this is where the image would form. And in fact, this is how telescopes work. So this isn't just a silly, trivial example. The way that modern telescopes work, they don't use lenses because lenses are quite hard to make if you want to make them really big. Instead, they use mirrors. And in fact, the mirrors that modern telescopes use, they are these concave mirrors, but they're made up of a ton of little chunks, a bunch of little, often hexagons, that are all mini mirrors that can move slightly. And in real time, they adjust themselves because of the fact that there's turbulent flow in the atmosphere. So they have a laser that measures the turbulent flow and adjusts all of these mirrors in fractions of a second all night long in order to keep the image focused on that focal point. And that focal point is where you put all of your electronics that, similar to a digital camera, capture the image from space. Okay. So then lastly, in chapter 19, we should talk about color and then this related idea of dispersion. So we've all seen this idea that, and it's illustrated well in this album cover, that white light can be split into colors using a prism, right? So in the previous section, we were looking at prisms in the context of lasers. We had one problem where we shone a laser onto a prism and we saw how that laser light was bent. But a laser is a very special device that creates only light at one wavelength. Well, in reality, you can have more, but typically we think of a laser as just one wavelength of light, one color. And so we only have to think about Snell's law for one color. Remember, Snell's law is N1 sine theta 1 equals N2 sine theta 2. But it turns out that the index of refraction isn't just a number for a material, it's actually a function of its wavelength. So different wavelengths of light will experience their speed changing in different ways when they go through a material. Some colors will really slow down, whereas other colors won't slow down quite so much. And so in fact, we can see in this picture that the red light isn't bent very much. So we can see that the index of refraction for red is less than the index of refraction for blue. So generally speaking, higher frequencies of light, the photon is having to sort of vibrate more frequently. So that would be like blue light. That those frequencies have a harder time traveling through materials, right? You can kind of imagine if you were trying to wiggle side to side as you like swim or something, that the faster you move side to side, the harder it would be to swim. It's very similar with light. The higher the frequency, the harder it is to travel through a material. And so that light that has a harder time traveling through the material will bend more when it is exiting. And so we get this order of the colors coming out where the red is bent the least and the blue and purple is bent the most. And that's what it means when we say dispersion. So dispersion is this idea that the index of refraction is a function of the color of light or the wavelength. Okay. And remember, I'm speaking about all of this in the context of light because chapter 19 is about optics, but we can do the same thing with sound. We can do the same thing with water waves. Anytime we think about a change in the material that a wave is traveling through. So when the sound travels through the air and then it has to pass through one of these seats and it changes material, that in that change of material, we have refraction and that for any material, the way and the amount it refracts, which is based on the index of refraction, will be dependent on the wavelength of the light. So higher pitched sounds might bend differently, and in fact will tend to bend more when passing through material than lower pitch sounds. It's just more evident in light because we can see light very easily. So we can look at these rainbows. Whereas sound, it's harder for us to kind of simultaneously hear all of these sounds and see where they're located in space, if that makes sense. Okay, so what we can do, and this is actually going back to Isaac Newton, so our friend from 3A, we can see him showing up again here. This was something he was obsessed with, was that we can shine white light through a prism and we get the red bending the least, the purple and blue bending the most. And if we shine those colors back through a symmetrical prism, they actually will recombine and produce white light again. So the process is reversible. We just have to invert this prism so that all of those Snell's law angles happen going backwards. We get to the same initial condition, which was just all the colors mixed up, which is what white light is. But that if we in between block one of the, all of the colors except one, so in part B, we let only green light through, then only green light comes out of the second prism, which seems obvious to us today, but back in Isaac Newton's time, that they thought that was crazy. They thought that when white light entered the prism, it was somehow interacting and creating different colors. But by showing that just allowing one color through, that color doesn't change, we see that that's not what's going on. That really white light is this superposition of all these different frequencies. And so I give you in the slide here just some approximate wavelengths for different colors in case you need to use them for the homework or something. This is an example of something that would be either given to you or you would have to calculate on the final. Okay, and so here's what a dispersion curve actually looks like. So again, this is dispersion. You can see that we have wavelength on the x-axis, so that's our independent variable. And for different materials, so for example, this upper blue line is for flint glass. I don't really know much about different kinds of glass, but there's apparently some sort of glass called flint glass. And you can see that for purple light, it has an index of refraction of 1.60, whereas for this deep red light, it has an index of refraction of maybe 1.57. So dispersion is a small effect. It's only changing indices of refraction typically at the 1% to 0.1% level, but it's enough to make rainbows and such. So, it's obviously visually, phenomenologically important. And you can see that some other type of glass has a different dispersion curve. Okay, so the rainbow here isn't necessary. It's just to show you where the colors are corresponding to the wavelengths on the x-axis. And so you might be expected to read one of these diagrams. I guess not for this class, because I've said this won't be on the final either, but you might in general be expected to read one of these diagrams and find the index of refraction for some wavelength, and then determine how that wavelength would refract using Snell's law. So once you've got the index, you can just plug it into Snell's law. Okay, and so this gets at, understanding why rainbows form. So this is actually a picture from somewhere in Irvine, and you can see that we have one rainbow here, and we actually have a second rainbow up here, and we can understand where both of them come from. So there's actually always a second rainbow if you see one rainbow. It's just that oftentimes the second rainbow is too faint. We'll talk about why that is. So the way that a rainbow forms is that you have little water droplets. So you could see how you could maybe write a combination problem using what we learned about droplets from chapter 9. But white sunlight enters the droplet, and since there's a change in material from air to water, and water has a dispersion curve as well, what that means is that the index of refraction for each color in water will be different. And so these colors will separate. And the light is going to reflect off the back surface of the droplet. And you can see that most of the light actually does refract. So most of it goes through the droplet because these droplets are almost transparent. But a little bit of it will reflect off the back. And then a little bit of it will reflect off the bottom here. And so you can see that we end up with due to both of these reflections and the refraction, we end up with these two angles. So red light coming out at a 42.5-degree angle from however the sunlight was entering, and blue light coming at a 40.8-degree angle. And so the difference in these two angles of about 2 degrees tells us that this separation across the rainbow is an angular size of about 2 degrees. So if you know how far away the rainbow is, then you can measure that thickness and divide them using the small angle approximation, and that should give you whatever 2 degrees is in radians. Just thinking about how the sine function works. And so whenever you see a rainbow, what's happening is that there's some sunlight behind you. You'll generally just see rainbows when the sunlight is behind you. And there's some abundance of water droplets in the air, enough of them that a significant fraction of the light actually reflects off the back of the water droplets. That's the limiting factor, since most of it will tend to go through them. But if enough reflects off the back, then due to the dispersion, so the different indices of refraction of these light waves in water, the colors separate, and so we'll see red always at the top and blue and purple always at the bottom. Okay, and we can see that here. So the red at the top, the blue and purple at the bottom, which means that if you're standing looking at this, the sun should be roughly behind you. And you can see that this process is something that we can rotate around the water droplet and we would still have happen, which is why you'll sometimes see people saying that rainbows are circular objects. Now, in reality, it's hard to see that due to the fact that the ground exists. But if you just went out in outer space and had a big cloud of water droplets and let sunlight shine through them from behind you, then you would see a circular rainbow, perfectly circular. Okay, and I guess I forgot to put a slide about it here, but the light can, let me see if I can draw it. So the light can do something like this and have an extra reflection inside, and that's how we get the second rainbow. So in order to have that happen, you have to have a really large number of water droplets, enough that the total amount of light coming from that triple bounce is sufficient to be visible to the human eye. And so there's always a second rainbow, like I said. It's just that usually it's not visible because there's not enough water droplet material in the air, and there's not enough sunlight at the right angle for you to see it. So, be on the lookout, and you can actually predict what the difference is in this angle. So you'll always have the same difference in this angular position. And that's just based on the geometry of the light reflecting in the little water droplets. Okay, and so then this is a slightly different topic, but the book includes it. So we can have filters, and a filter is just a transparent material that only allows one color through. So what happens with a filter is that, for example, this red filter, is that it absorbs all wavelengths of light except for red, and it lets red pass through. Similarly, the green filter absorbs all wavelengths of light except green, and it lets green pass through. So you can see that if we layer the two on top of one another, that nothing can pass through, because all that passes through the red filter is red, and then it gets to the green filter, and that red light isn't green, so it doesn't pass through. So we have the overlapping region as black. And this is in contrast to paints, which are an example of a situation where all of the colors are absorbed except for some color that's reflected. And so for red paint, the red wavelengths are reflected, whereas the other wavelengths are absorbed. For green paint, the green wavelengths are reflected, whereas the other are absorbed. So reflection is an additive process. If we mix them together, then we reflect both red and green, which the human eye perceives as brown. So you can see some examples of mixing red and green here. So this is the difference between additive and subtractive color addition, which, I don't know, if you're interested in art, you may have heard about. So it's just a function of, is the light being transmitted or is the light being reflected in the situation? And this is a good time to mention that colors like brown and pink and all of the colors that aren't in the rainbow that we have names for, that these are really just a function of our brain. So the way that we interpret combinations of light. And if we had a brain that was able to pick apart individual wavelengths at a better, degree of accuracy, then we wouldn't perceive brown. We would just perceive, oh, we have red lighting up and green lighting up. You know what I mean? So these combination colors are an artifact of the human brain and its ability or its lack of ability to distinguish different wavelengths. So the only, real, in the sense of physics, colors are the ones that have a wavelength associated with them, which are the colors of the rainbow. But of course, the other combination colors are just as real. It's just that, it's only something we can talk about between humans. And so if we were trying to describe brown to our dog, they would not experience it in the same way. Okay. And then, so speaking of color filters like these red and green filters, so the atmosphere has some filtering ability. It mostly lets through visible light, but it filters out, other wavelengths, so infrared, ultraviolet, all those things. And you can see that for plants, they turn this visible light into energy, right, via photosynthesis. And we can talk about the absorption, so again, now similar to paint, of the chloroplasts or the chlorophyll, which, as you can see, absorbs heavily in the blue and red regions, and then is the color green because it's reflecting this green light back out. So this is an example of, reflective coloring in a situation. So the light's shining on, all of the chlorophyll on all these plants in Aldrich, and only the green is reflecting out back at us. Okay, so then the final topic in this section in chapter 19, before we take a break and then move on, is discussing why the sky is the color that it is. So in the case of the sky generally, that's blue, but in the case of sunsets, we see it as this deep red. And so this isn't related to anything we've talked about so far, but it's about color, so you should learn how it works. And so the way that it works is through scattering. And again, this formula won't be on the final, so don't be too scared. But so this is the formula for Rayleigh scattering, which is an approximation based on the particle size. So for very small particles, things like fine dust in the air and oxygen and nitrogen molecules, we can imagine, how does the light, as these light rays, how do they interact with these molecules? And it turns out that they mostly don't interact with them. That's why we say that the air is transparent. So for the most part, the light just passes straight through. But the atmosphere is really thick. As we learned in the very first chapter of this class, it has enough weight that we experience 15 pounds on every square inch of our body due to its pressure. So there's a lot of atmosphere above us. And that combined effect is what allows this relatively weak scattering of light. So the fact that the light can bounce off these particles, it's what allows it to have such a dramatic impact, dramatic enough that it dictates the color of the sky. So what happens, and you can see in this diagram, is that sunlight is pretty close to white in color. And so this white sunlight shines upon the earth and travels through the atmosphere. As it travels through the atmosphere, it bounces against all of the molecules in the air. And it turns out that light of a higher frequency, so bluer light, is more likely to bounce into the air. And that's dictated by this lambda to the fourth. So the intensity of the light that's scattered, so we can imagine that as sort of how much light is being bounced away in different directions, is related inversely to the wavelength to the fourth power, which means that the bigger the wavelength, the less intensity is scattered. So the shorter the wavelength, the more blue the light, the more intensity. So you can see that here, that the blue light has a greater intensity scattered than the red. That's why you can see it actually happens by a factor of 4. that there's more blue than red scattered as light travels through the atmosphere. And so if you're standing like this person over on the left, and you're looking somewhere in the sky that's not the sun, what do you see? You see the light that's scattered. You see the light that's bouncing off the air. And this light is predominantly blue light, because the higher the frequency, the more light is scattered. And this is only true for small particles. If the particles are bigger, like water vapor, then it actually will scatter all the light pretty much uniformly. This is known as Mie scattering. And so that's why clouds are white, is that they're scattering all the light uniformly. And so that's why, clouds and fog, those sorts of things are all white colored. So it's a different approximation of the same phenomenon. So if we assume that the particles are very tiny, we call this Rayleigh scattering. If we assume that they're bigger, we call this Mie scattering. And there's also a case in the middle, but that gets really tricky. But anyways, so then if we look at the sun directly, what do we see? Well, we see the rays that didn't scatter, which is predominantly redder colors. And if you're just looking at the sun in the sky like around noon, the atmosphere above that section of you isn't very thick. So some of the light does scatter away and make the sky blue in every direction, but not enough of it scatters away that the sun looks red, so it looks something in between, which is why it looks yellow. But when the sun is just about to set, the light has to pass through significantly more air, right? Above you, there's just this much air, but to the side of you, there's like this much air because of the fact that the Earth is a sphere. And so as the light travels through that extra length of air, it scatters out more and more of the blue, and so the sun looks more and more red. And there's a really cool phenomenon. So my dad was a sailor, and so I asked him one day when I learned about this in physics class, and he was like, "Oh yeah, we used to see that." So there's a phenomenon called the green flash, which is that if you're out in the middle of the ocean, that there's a particular time right around sunset where you can actually see that transition from the blue, yellow to the red, and it looks like this green burst of light just for a moment. But you need an incredibly flat horizon to see it, because it's a very weak effect. But anyways, so we see that there are all of the colors of the spectrum that are dictated by scattering. And this is also why if you live somewhere that has a ton of pollution, like I know Mexico City is famous for this, that you get really beautiful sunsets because you have a lot more scattering happening. So you get a much deeper red. Okay, so that's the end of chapter 19. Are there any questions before we take our short break in the middle? Okay, so we'll leave it there. And I'll go ahead and open up the next slides, but you can take 5 minutes to relax a little bit.
Same one I asked about yesterday, I still don't understand, it's the same like on the ground too and angles, I'm just like.
Did you try it out and it didn't work?
Oh, it worked,
Oh,
it was
okay.
just that I don't understand how you've got like the idea of like the normal and that.
Yeah, so it's tricky for this. I can try to find a deeper explanation, but okay, when we're looking at so this is a solid glass tube. So when we're looking at the front surface, this is flat and vertically oriented.
Yes.
So the normal will be horizontal
Because it's always pretty.
because it's always perpendicular to the surface. That's what the refraction is happening. So this dashed line is the normal
for this first refraction.
Okay.
That's causing the ray to go from here to here at a different angle. But then the ray wants to pass through the glass.
Yeah.
And so it wants to go from the glass to the air through this surface. And so this surface is horizontal, so the normal is vertical.
Okay.
So that's this dashed line that you labeled new normal. And so then, we have to think about what's the angle from this ray here in the glass to the new normal, and you labeled that theta c. So if that angle happens to be theta c, the critical angle, then that's when this light would be bent 90 degrees. And we just say, well, if it's bent 90 degrees, it's not really refraction anymore, it just follows the law of reflection. So it's the same.
Okay.
And then the hard part is getting from the angle you get from Snell's law here, which is the left angle in this triangle. And then we see that there's a right triangle. So this is the,
So I guess why did I use this? I guess why would I use this then? Like the critical angle formula
so
in this case?
the critical angle formula tells you what angle you need for this theta c for that bit in order to have it reflect inside. If this angle is any bigger, it'll also bounce down the tube. But if it's any smaller, then it'll travel straight out.
Oh, because we want it to bounce.
We want it to bounce
So
with
then
the
you
tube.
need to use this.
Exactly.
And then fine.
And then that lets you find theta naught. And so theta naught, if we shine it more directly, then that'll make this angle bigger.
Okay.
So that'll make it more easily reflect down the tube.
Okay.
Does that make sense? So it's like, it's a weird thing, but this is practically what you want to do. Because if you're thinking about, let's say you have a fiber optic cable, which you might use in the surgery, then you need to shine the light into the cable, and that's this theta naught angle they're wanting you to think about. But in order to know how we have to shine it in, we need to think about this perpendicular
Okay.
line angle, because that's the thing that Snell's law is talking about.
Okay. And then like this example that we did in class, I tried to solve it myself yesterday, and I was able to get like the idea that like this angle is theta 1 under here.
Mhm.
But then I was just wondering, like, why wouldn't I be able, like, I knew that in the lecture you said that the theta 2 or 7 for here, this angle, why can't you just be this one? Because isn't this also against the normal? That makes sense?
So it has to be, you're saying, why can't it be from here to here?
Yeah.
Yeah, so in Snell's law, we generally want to choose the reference angle. So the angle between 0 and 90 degrees, so that we don't have to worry about plus and minus signs. So we could use that angle, but then there would be some minus signs floating around, which would just be a little annoying. It wouldn't be the end of the world, you could still solve, right? If an angle and its supplement, the signs of both of those will be the same number, just with some minus signs. So this one, whatever number you get for sine of this,
Yeah.
you would get the same number here, but with a minus.
Oh.
So it wouldn't really affect your equation.
You would just make it.
You would just have to be like, okay, this minus sign is, you know what I mean?
Okay, okay, all right.
Yeah.
All right.
No problem. Great questions. Yes.
I did ask
Yeah.
just start like comparing. Yes, I'll try to better. And then take one side.
Uh-huh.
And then like some of your mind.
Uh-huh. And that's because in reality, this is a great question. In reality, filters don't just let in. So if you imagine the wavelengths on the x-axis, in reality, it's not like 0, 0, 0, 1, 0, 0, 0. In reality, they're going to be some curve. So there's some range that they let in. So if you have things that are close together, like yellow and green, they'll overlap a little bit, and it'll let that overlap. Yeah, so this is really important in astronomy. So if you ever take an astronomy class, I don't know, or if you just read about it, then you'll learn there are all these, they call them bands. There's like L band, K band, but they're just letting different chunks of light through so that you can figure out what colors stars are, which tells us about their temperature, thinking back to the radiative or Maxwell, sorry, Planck. And it tells us about like through the color, it tells us about their age and how big they are. A lot of
Okay, so we should jump back into it and finish off the summer strong with the last little chapter here. So let me actually move these controls. So just to give you an idea of what I did, I've added this little sun symbol to the top right to the slides that you actually need to know for the final. It's not that many of them. I think there are only maybe 5 slides like this. But anyways, so chapter 20 is all about what do we do with our newfound optics knowledge. And so what we want to do is we want to build stuff. We want to build equipment that lets us do things that we couldn't do with our normal human eyes. And so, one example just to get your brain thinking about this is a pair of binoculars. So with binoculars, we have 2 lenses, right? We have one lens up at the eyepiece and one lens down on the other side, which we call the objective lens, very similar to the notation in a microscope. And we use refraction, actually. Some binoculars use mirrors here, but oftentimes we use prisms to bend the light all the way around through the handle in order to get it centered on that second lens. So you can see that the light enters from the outside, it's focused by this first lens, some amount, and then it's bent around just to make it more conveniently oriented, like with respect to your eyes. And then it's focused again by the second lens, and our eyes see that light from the second lens. So in order to understand how something like a pair of binoculars or a refracting telescope or a microscope, all these different things, in order to see how they work, we have to think about what happens to the thin lens equation if we have 2 lenses in a row, talking to one another. And so that's what we have to know. That's what we have to learn today, basically, the last thing in this main thing in this class. So the way that it works is that we just do the thin lens equation twice, but we have to be careful in regard to where we're measuring those distances. So for example, we would do the thin lens equation. So if this is lens 1 and this is lens 2, so we first do the thin lens equation for lens 1. So we can see that there's some object length s, and that there's some focal length f1. And so we can say 1 over s plus 1 over s prime equals 1 over f1. And actually, I'll call this s1 just to help ourselves, and this s prime 1, just because we're going to have all of these things for the second lens as well. And we find that way out here, that this is where s prime 1 is. So we use the thin lens equation for the first lens, we find the image length, and in this case, we would get a positive number. So that tells us it's to the right, it's a real image. And we call this point in the diagram P prime. However, the light from this point P prime isn't actually what our eyes see, because it now has to pass through the second lens. So now what we do is we say, how far is this point P prime? So the image from the first lens, how far is it from the second lens? We call that S2, right? That's the second object length. And now that second lens has a focal length. And so we use the thin lens equation again. We say 1 over S2 plus 1 over S2 prime equals 1 over F2. And we can solve this if we know F2 and we find S2 from the first lens. So we can get this position of the final image. So in this case, we would find a negative number just based on this diagram. And so that's telling you that's to the left of lens 2. You see, once you start doing the thin lens equation for lens 2, we have to measure all distances with respect to lens 2. This is the thing people most commonly get wrong, I would say, is that when you do the thin lens equation for lens 1, everything is with respect to lens 1. but you have to take that image length you find and turn it into a distance away from lens 2, because then you're going to do the thin lens equation again for lens 2 with that new object length. Okay, and so this S2 prime that we find, this is what your eye actually sees. So looking through this second lens, we see the light focused by the first lens. So the first lens creates this real image at P prime, that black circle, and then the second lens creates a virtual image at P double prime, where this blue dot is. So this is what your eye actually sees when you look through this. In this case, they call it a microscope, but binoculars work very similarly. Telescopes work very similarly. They're all kind of the same under the hood. It's just a matter of details. Okay, so for the most part, this all works the same. And so we have to think about the plus and minus signs, right? In this case, both of these are converging lenses just visually. So the focal lengths for both of these would be positive. And we see that we got a positive image length from lens 1, but we got a negative image length from lens 2. So that, remember, the image length is positive if it's on the opposite side from the object, and it's negative if it's on the same side from the object. But I want to add one more bit of detail to this that I alluded to yesterday, which is that the object length we tend to think of as only ever being positive. However, the object length can be negative if it's due to a lens ahead of the lens that you're interested in. So for example, in this situation, running out of space here a little bit, but if we have these two lenses, let's say that this is our object, and that lens 1 creates a new image over here. So let's say that this is S1 prime over here, this distance. Now, the light that lens 2 sees is apparently originating from the right side. Do you see what I mean? The light that lens 2 sees, which is coming from lens 1, is being focused somewhere that's on the wrong side of lens 2. And so we would have to find this distance, right? We would have to use the separation of the lenses to figure out how far lens 2 is from that image. And this is what we would call S2, and it would be negative. So the object length for this lens 2 in this situation would be the negative distance from lens 2 to wherever that image forms on the right side. So just to give you some numbers here, so let's say that from lens 1 to this real image over here, maybe we found that this was 5 centimeters. And maybe we're told, or maybe we measure that the distance between the two lenses is 3 centimeters. So in that case, when we go to do the thin lens equation for lens 2, we would call the object length -2 centimeters, right? 5 minus 3. But then we have to say that it's negative since it's to the right of that lens 2. And so then let's say that the focal length for this lens, I don't know, let's say that it's 10 centimeters or something. So in that case, we could do the thin lens equation for lens 2. 1 over S2 plus 1 over S2 prime equals 1 over F2. And we could use this, we plug in -2 for S2, we plug in 10 for F2, and we could solve for what S2 prime is. And that would tell us the position of the image that we would actually see through this combination of lenses. And if it were positive, that would be to the right of the lens. And if it were negative, that would be to the left of the lens, right? And if it were positive, that would tell us that this would be a real image, whereas if it's negative, that tells you that it's a virtual image. Okay, and then you could immediately ask me, okay, Cannon, what if I have 3 lenses? Or maybe you don't want to know the answer to that, but you just do it again, right? You just keep going. You start at the first one, you work your way onward. In some problems in the book, or that I might give you information related to the last lens, and then you would just have to work your way backwards. You would have to start at lens 2 and then figure out how that relates to the image from lens 1. And then you could turn that into where the object is, for example. So if you know where the final image is, you might be asked to turn that into where the initial object placement is. It's just a matter of going either from the first lens to the last lens or from the last lens to the first lens. You're always going to be doing one of those two operations. Okay, so in this set of diagrams, everything is a little bit more labeled, so we can see a better example. So if we call this, again, lens 1 and lens 2, and we say that they're both converging lenses so that the focal lengths are positive, then for lens 1, what we do is we say this 1 over S1 plus 1 over S1 prime equals 1 over F1. And we see in this diagram that S1 is 35 centimeters. F1 is 20 centimeters. And so we could then solve for what S1 prime is. And we would find, as it's labeled here, that this is 46.7 centimeters. So this is what we would generally be solving for. And that's where this line is on the diagram. So that's the image from the first lens. Now what we do is we look at lens 2, and so we have to say 1 over S2 plus 1 over S2 prime equals 1 over F2. And so in order to get S2, we say we have the separation between the lenses, that's 75 centimeters, and we found the image from the previous bit of work with the thin lens equation. So then we just subtract those, and we get 75 minus 46.7, we get 28.3. So that's our object length for the second lens, and it's to the left of the lens, so that's a positive object length. We don't have to worry about the minus sign here. And then again, generally we would be solving for S2 prime using the fact that the focal length here is 15 centimeters. And in fact, they do solve this for us and find that that image occurs to the right, so positive, 31.9. centimeters. And so that's this final image here. So what this is saying is that if we put these two lenses in a box and called that box an optical instrument that we shine in light. So if we put these two lenses in a box with lens 1 and lens 2 in here, and we have our object that's 35 centimeters away, that it'll produce an image that's 31.9 centimeters from the other side of the box. Okay, so once we do the work of analyzing one of these systems, we can just think of it as a black box, right? A mystery object that just takes in an image and spits out, takes in an object and spits out an image. And the magnification equation for something like this is quite nice. We can just multiply the magnification from the two lenses. So remember that the magnification from lens 1 is just going to be negative S1 prime over S1. The magnification from lens 2 is going to be negative S2 prime over S2. And so the total magnification is just S1 prime, S2 prime over S1, S2. And so, we could plug that in for this set of lenses just to show you what this looks like. So S1 prime was this 46.7. S2 prime is this 31.9. S1 was 35. And S2 was the 28.3. And so putting all of this together gives us some magnification. You can see that this has a slightly positive, like slightly more than 1 magnification, but not by very much. I didn't calculate this ahead of time, but it looks like it's, 1.5-ish or something like that. Okay, any questions about lenses in combination? I know it's quite a bit. Yes.
Is the magnification always going to be positive than when you have two lenses instead of the negative sides of the shape cancel?
So it can be, but remember that our S primes or our S's in the case of multi-lens can be negative. So in the example of this now heavily written on diagram, our S1 and our S1 prime are both positive. Our S2 is also positive, but our S2 prime is negative. And so you can see that the object is an upright arrow, but that this virtual image that we see is an upside down arrow. So that tells you that the overall magnification in this situation is negative. Whereas here, they kind of cancel out, right? Lens 1 has a negative magnification, it flips it, but lens 2 also has a negative magnification, it flips it again. So it really depends on your system, but you can see that it can go either way. Yes. Yes. So so S2 prime is the 31.9. That's what you're interested in? Okay. So the reason it's positive, we can solve the thin lens equation down here, and we see that like, you know, 1 over 28, whatever, plus 1 over 31. If we just add those two fractions, we get 1 over 15. So that's satisfied. And so that's what's telling us mathematically that S2 prime is positive. And then interpreting that is just saying that we have this image, the blue circle, sorry, we have the object, which is the blue circle, which is the image from lens 1, and it's outside the focal length of lens 2. And since lens 2 is a converging lens, anything that's outside the focal length is just going to pass on through and produce a real image on the other side, right? If this blue circle were inside, so if it were closer to lens 2 than this point labeled F2, which is the focal point, the inner focal point, then in that case, we would get a virtual image from lens 2, and our S2 prime would be negative. We would have something on the left of lens 2. But in this case, it's outside the focal length, so it just passes on through and makes a real image on the other side. So everything's positive. It's a very good question. It's good to see why things are true mathematically, but also try to build your intuition for it, so that if you mess up mathematically, which I know I do frequently, then you can at least feel like, whoa, that sounds weird, once you think about it a little bit. Okay, any other questions on this section? Yes. Mm-hmm. Correct.
So it's both S and it's negative, or like it's both S.
Correct.
And then for S, it's positive when it's to the left of the lens, and then it's positive negative when it's to the right of the lens.
Exactly. And you know, you can think about if you just have one lens, then you should just call whatever side the object is on the left. Okay, and then that's positive. But if you have two lenses, then you say the object is to the left of lens 1, but then lens 1 might do some funny stuff and force the object for lens 2 to be to the right of it. So that's why we have to think about negative object lengths only in the context of multi-lens systems. Yeah. Good. Any other questions here? I know this is a lot. So I'll probably make a little tutorial or something on this. I'll either find someone else's or make one, just because I do really want to emphasize that I want you to know this for the final, but I know that we haven't gotten to do much of it. Okay, so just to give you an example to build intuition, so we have this diagram and they want you to say the second lens in this instrument would cause what to happen. Okay, so we have light entering lens 2 from lens 1. And so would it cause the light rays to focus closer than they would? Would it cause the light rays to focus farther away than they would? Would it invert the image but does not change where the light focuses, or would it prevent the light from reaching a focus? What do we think? So raise your hand if you think A. What about B? What about C? What about D? What about, I don't know. Okay, good. I guess not good, but thank you for being honest. So this is a diverging lens. And so generally it's going to cause the light to separate out. So even though it's being focused by lens 1, this second lens is going to cause the light to spread out. And so it prevents it from coming to a focus, creates a virtual image. Okay, so now this isn't going to be on the final, but I think it's good to see just a little bit of. So we talked a little bit about a camera obscura, which is just Latin for a dark room, where we have an opening and it allows us to see an inverted projection of the outside world. And that's basically what a camera is. So a camera is just a miniature dark room that you can carry in your pocket that has an opening, which is fairly small, which is known as the aperture, that allows light to pass through and be focused onto film or these days some digital sensor. And so we can see that what happens with a camera is that we have light coming through the first lens, and then depending on how we adjust that that lens, like in nicer cameras, you can actually turn a wheel and change the distance between the two, that we shorten or lengthen the separation, which changes the focal length of the overall lens. And so as a result, we can cause different parts of the image, so different distances away, to be in focus based on where we move these two lenses in relation to one another. And for a camera, we have a nice relation that the object length, so how far away something is from you, is related to the magnification by the effective focal length of the camera, so the overall focal length. And to get that overall focal length, we would need to think about this lens system as a black box and say how far away is the object, how far away is the image, and then do one thin lens equation for that system. We can also ask how the intensity of a camera is related to both the opening size and the sorry, this is a little confusing notation here, but the opening size and the focal length of the camera. And by taking a ratio of them, we get something known as the F number, which is inversely proportional. So it's inversely proportional to the intensity. Okay. And so for a camera, you'll often see these sorts of numbers associated with your lens, and it's often something you can adjust. And so this over 1.8 is just a terrible notation to tell you that the f-stop or the f number is 1.8. So in the top picture, it's 1.8. In the bottom picture, it's 22. I don't know why they use this notation, but that's just telling you something about the ratio of the focal length to the diameter of the opening. And so for a larger f number, we actually have a lower intensity. And it's kind of hard to see in these pictures because in photography, they often change how long the exposure is. So if you have a low intensity open for a long time, you'll gather a lot of light and your image will look bright. So here we have a high intensity. And by changing our exposure time delta t, we can change how bright the image is. So it looks to me like all these images have had varying delta t's with varying exposure times that cause them to be a similar brightness on the film, which is something that often is done automatically by modern cameras. But you can see that when we have a smaller f number, that also corresponds to a smaller focal length, depending on how this is being handled by the camera internals. And so we get only things up close coming into focus. So commonly in photography classes, they'll just teach you that if you want to create this nice blurring effect, which is often thought to be attractive, then you just want to use a smaller f-stop or a smaller f number, that these mean the same thing. And you then have to have a longer exposure time in order to get the same brightness in your image. And this is a good time to talk about digital cameras. I made the question related to them extra credit, I think, on the homework, but you allow light to shine onto some light detectors, and light detectors can just only tell you is there light or is there no light. So in order to take a color digital photograph, you have to put filters on top of some of these sensors. So on some of them, you only let blue light through. And so if it says, hey, there's light, then that's telling you that there's blue light in that part of the image. Some of them you only put green, some only red. The reason we pick these three is that those correspond to how humans can detect color. And by making those very, very tiny, we can have a reasonable enough resolution to make digital photography a viable alternative to film-based photography. And then in the last 5 minutes, we can talk about the eye. So the eye, it's a really complex and beautiful thing. So this demonstrates one way that the eye evolved to give rise to these complex camera type eyes that we have in humans. So just going from light sensors, which are common in bacteria, to creating these eye cups, which are just regions that have sort of a concave structure with lots of eye sensors, to those filling with fluid, which would be a naturally occurring process. And then those layers of fluid developing different indices of refraction, since that's evolutionarily advantageous via focusing the light, until you eventually get a lens. But evolutionary biologists actually would tell you that the eye has evolved independently at least 40 times over the course of animal and other creatures' evolution. And so if you go out, especially in sea creatures, you'll find a bunch of different types of eyes. And my favorite eye is the eye of the scallop, which actually uses a parabolic mirror. So I don't know, fun fact. It's totally different from a human eye or from any of the eyes shown in this picture. And so here's an example of a human eye. Like I said, we have the lens and we have these ciliary muscles that can tug on the lens to change its radius and via the lensmaker equation, change its focal length, allowing you to view objects at different distances. This just shows you a distribution of the rods and cones in the eye. So you've probably learned in a bio class that the rods are, as you can see, there are lots of them. So they're very good at light collection, but they can only tell you if there's light or not. So they don't have color information. Whereas the cones are only concentrated in the sort of central point of your vision, but they can tell you if there's color or not. And so that's why your peripheral vision generally is better at night, and it also is less adept at distinguishing colors. Also, I'll highlight that there's this blind spot, which is where the optic nerve is, where we have no rods or cones. And so our eye is actually constantly adjusting and focusing on all different parts of our environment. And then our brain stitches all of those images together. And each of them has a little dark spot where our optic nerve is, but our brain stitches them all together so nicely that we don't even notice that we can't see somewhere. So while I'm looking at you, there's some blind spot constantly over some of you, but I don't even notice. And so, like I said, some cones are sensitive to blue, some to green, some to red. The green, this is a dyed image. The green things are cones. Or sorry, the green things are rods and the purple things are cones. You can tell from their shape. And so, yeah, this is just an example of some of the eyes that you see in the world of animals. Some of them use just optical sensors, some use lenses, some use mirrors, all different types of things. So every optical instrument we've seen so far in the class, some animal is using it as an eye. And like I said, the far point for vision, for normal vision, is infinitely far away. The near point is around 25 centimeters. We'll skip over some of these examples. It turns out since eyes are spherical, they can have different focal lengths on the vertical axis relative to the horizontal axis. So if you go to your doctor and your eye doctor and get a prescription, what you'll see is this first section. So this is just, I forget which one, but one of these is like your right eye and one of these is your left eye. It's just some silly Latin stuff. But this first correction is just the power of your eye in terms of a spherical lens. And then the second number tells you how that power is different in one direction versus the other. So we call it the cylindrical correction. And then this axis tells you where that power is the largest. So if this axis is 100 degrees here, that tells you that at this 100-degree angle, that's where we have this +3 power. So in this case, 2.5 + 1/2. And this is why you can't just go to a vending machine and buy a pair of glasses, because everyone who needs glasses has a different cylindrical correction at a different angle. So there are like infinite number of combinations. And so that's why they still have to be machined for you personally, which is part of the reason they cost so much, also because of
monopoly economics. But anyways, there are a couple of slides on magnifiers. I do want to cover them. It's just 4 slides here. So I'll probably release a mini video since we didn't get to them. Sorry about that. But anyways, I encourage you to check out the rest of the slides. There's some information on microscopes here. Sorry again, but we'll have to leave it there. Thank you for joining me on this journey through this huge amount of material for Physics 3B. Please look on Canvas for any announcements as we try to wrap up the class, and email me if you have any issues. Oh, and fill out course evaluations if you can. That'll let me do this again if you think I was decent at it. Anyways, I'll leave it there and hopefully see you for the final.